I actually couldn't have asked for a better talk to be placed before my talk, because now you know all the importance of using these kinds of like vector or functional or polynomial commitments for building efficient proof systems, right? And I can just concentrate on the security of a specific family of polynomial commitments. So that's what my talk is going to be about. It's based on this recent paper that we had. I'll list the collaborators later. And there's also some, mumbling that I will have on the foundations of the security of these polynomial commitments. So let's just take a look at what is a polynomial commitment, right? We have this interactive protocol between a prover and the verifier. And the prover has this polynomial, right? Here we have a univariate polynomial of degree n. So we have n plus 1 coefficients, fn for the leading monomial and f0 for the constant term, right? And the prover wants to commit to it. It's an extension of the classical notion of bit commitment from cryptography, where the prover just sends some C over to the verifier, right? Then the commitment phase is over, might be interactive, might not. And later in time, the verifier will have this urge to ask for evaluations of the committed polynomial. So it will have a field element, alpha, send it to the prover, and the prover will evaluate. And together with the evaluation, it will provide a proof, convincing the verifier that it is the correct evaluation of the committed polynomial, right? So the way it's written like this, like if you were to present it to a non-cryptographer, it makes no sense, right? Because I didn't specify anything that would make the scheme interesting, right? So what we care about is the efficiency requirements. We want the commitment and the proof to be very short, right? So the commitment should be much shorter than the number of monomials that we have in the polynomial, and the proof optimally too, and it should take much shorter time to verify the proof than to evaluate the polynomial, right? Because the way we think about it in the wild is we have polynomials that have 2 to the 20, 2 to the 30 monomials, right? It's like huge polynomials, and you want the verifier to be some very big device that doesn't have to evaluate these polynomials, okay? So far so good. Now, okay, so this notion was presented in a paper by Kate, Zaverucha, and Goldberg, right? Very influential paper. They put forward the notion, and it was independent of these SNARK compilers. So in particular, they considered much weaker notion of security for these schemes than what you would want to have for these compilers from PIOP to SNARK. So what is the basic notion? So the basic notion is so-called evaluation binding, right? Now we're interacting with the cheating prover. So the cheating prover pulled out of the hat a commitment, right? It doesn't have to do anything with a polynomial and just sends it over to the verifier, right? And then we would want to have the property, like the bare minimum, right? That later, when a verifier asks for an evaluation at alpha, the prover will not be able to answer in, like that the function at alpha has two distinct values, z and z prime, and provide accepting proofs for that, right? So this is the bad event when it would actually succeed in convincing about two values, right? So what would this guarantee? Well, it would guarantee that the prover is bound to a function, right? And you might think, okay, this is good enough, right? We mostly work with finite fields. Over a finite field, any function is a polynomial, so where's the problem? Well, the problem is with the degree of the function, right? Like any function is a polynomial over a finite field, but it might have, arbitrary degree. So what we want that the function is a polynomial with some prescribed degree bound, right? And that's the notion that people call knowledge soundness, or for short extractability, right? So it's like a stronger guarantee where we want that if the prover manages to convince the verifier with some probability epsilon, right, then we can actually show that it's bound to some polynomial of some fixed degree, right? So this is what we want. At this moment, hand wavy, I'll go towards talking about extraction a bit later, but please interrupt, ask if there's anything unclear. Okay, so these are the security notions. We would want knowledge soundness, extractability to work well in this compiler paradigm. And let's take a look what was known about this like KZG family of schemes that right, like people actually use a lot in practice. So quite a lot has happened, but it took a long time. So the original paper, KZG, in 2010, they introduced the scheme and proved the weaker notion of security, evaluation binding, under a very standard assumption, strong Diffie-Hellman, right? So good, you know, like it was good enough for their application that they had in mind. And later, Campanelli et al., Lipma et al., they showed that actually this univariate KZG, the original scheme from 2010, is extractable, but in these idealized models. So this algebraic group model, or its more recent extension to so-called AGM with oblivious sampling, and that is unsatisfactory. I'll talk about it in a moment. So there is okay, so this univariate KZG, it's used in practice, for example, for Plonk. It's used for Halo 2. We have other class of proof systems that rely on multivariate or multilinear polynomials, like these sum-check-based approaches like Spartan and many others. So for that, you would need a polynomial scheme, polynomial commitment scheme, that supports evaluations of multilinear polynomials. And that we don't really get out of the original univariate scheme. However, like quite soon after the KZG paper, there was this Papamantu, Shi, and Coulter in 2013. So they introduced a multivariate variant of KZG and showed right away, like again, it was 2013, so no application towards SNARK in mind. So they showed that it's evaluation binding. I have here an asterisk. So they didn't really show evaluation binding. They showed evaluation binding what I would call on average. So if the verifier samples the evaluation point uniformly at random, then it's hard to break the evaluation binding property. They used SBDH, so like the strong Diffie-Hellman assumption in the bilinear setting. Morally, it's pretty much the same proof as the evaluation binding of the univariate scheme. And right, yes?
How do they use the fact that it's a random point? This is to make it the assumption standard? Is this, what's the...
Yeah, so like for the reduction...
Yeah, but like, I guess you could prove it with... evaluation binding is a very strong property, and because you're giving the... So I guess they could prove it also for not a random point.
So they can prove it for a non-random point, but for a different variant of the scheme. Right. No. So like so in that paper, they have a scheme. They call it like a randomized multivariate scheme. And the point is they kind of shove the on average into the scheme. So instead of in the evaluation binding, like for arbitrary evaluation point, right? Okay. And then, yes?
Considering the future that with the rise of quantum computing, how secure is it in the future with Diffie-Hellman?
So I mean, you hear this all the time, right? Like people are considering move to like transparent assumptions, right? Hash-based constructions, right? So if you are worried about like general quantum computing, then you shouldn't use this, right? And then question is like, how worried should we be, right? And yeah. So I think that like currently the sad truth is that like this is not post-quantum safe, right? But it's just better. Like there's a lot of algebraic structure. These things are extremely efficient, right? So that's why you would use it, over some hash-based construction, right? Like Frey, because the proof size is going to be ridiculously small. We'll see it in the construction, no Merkle trees. Okay, so good. I want to talk about, like how do you get extractability for this? And there was this Zhang et al. Paper from 2017. So they showed actually extractability knowledge soundness. However, under a non-falsifiable assumption, so I mean, who cares, right? It's an assumption. It's like somewhat comparable to the AGM. But the main issue that I would have with this is that they had to also change the scheme. So in order to use the assumption is power knowledge of exponent, you somehow need to run 2 instances of the polynomial commitment in parallel, right? And that you don't want to do as a practitioner, because like people are after optimizing the heck out of this. Like if I have a structured reference string of size of gigabyte, now it's like 2 gigabytes, right? So that's one of the main issues with this. So the real question was, so can we have a proof of extractability in the standard model? And Litma, Parizela, and Sim in Eurocrypt last year, they gave proof of knowledge soundness for univariate KZG under this new adaptive, rational, strong Diffie-Hellman assumption. And I don't want to be technical about the assumption. Like how I think about it is that it's like a interpolation-friendly hardness assumption. So we will see like some high-level idea how you would want to use it. And what we did, right? Unfortunately, the proof of Litma et al. This was the first proof. They had a lot of great ideas, but they were all like together. So we took it apart and showed that if you work somewhat more, then you can push that proof strategy to the multivariate setting. Even though you might need a slightly stronger assumption, so like their assumption is this interpolation assumption for univariate polynomials, you can have an analog for multivariate polynomials, and that would be the ARSDHN. Okay. And so this was presented by Kristina Mašková, one of our co-authors of the paper. So it was Juraj Belahorec, who's here, Pavel Hubáček from Charles University, Charlotte Hoffmann from IST Austria, Kristina from Charles University, and Martin Pastyřík. So let's take a look into like KZG. Good. I have enough time. So KZG, they came up with this amazing protocol. I enjoy how simple it is and like how efficient it is, and it's based on a very basic observation that if you want to convince someone about evaluation of a polynomial at a point, right, you can do it in an extremely cumbersome way just by moving to an equivalent polynomial identity, right? So if it holds that at this specific point, like this local property, that f of alpha is z, right, then what I have is that if I would take the polynomial f and subtract z, right, so this left side of the equation has a 0 at alpha, right? Because like f of alpha is z, so f of x minus z would 0 out at alpha. If it zeroes out at alpha, I can take out, I can factor out this linear term x minus alpha, and it will be left with some quotient polynomial, right? So instead of this local check, I do like a horrible global check, right? And you would ask, why are we doing this? Like, it's insane. It is insane, except, like if you want to build a polynomial commitment, right? Because if you work in the setting of polynomial commitments, we don't work with polynomials. We never want to send polynomials across. We will work with some short representations of polynomials, and then this check is very useful, okay? So, does this equality make sense to everyone, right? It's very simple. Now, good. So let's take a look, how do you construct a scheme, right? A polynomial commitment scheme like this. So I said on extractability of pairing-based polynomial commitments, right? So we need to use pairings. What are these pairings? So pairings are just bilinear maps. So we have this setting, the algebraic setting, where we have 3 groups, group 1, group 2. They are down there in the corner. So I have a G1, G2, and a bilinear map from G1 cross G2 to the target group. What is a bilinear map? It's just, like a nice map, right? It's bilinear, like, inner products. These are bilinear, canonical examples of bilinear maps. This is another example. If you take A and pair it with B, you will get a representation of A times B in the target group, right? So we can move from the source groups G1, G2 to the target group and preserve some nice properties like this, like linear properties. Why would you want to do it? Well, because you don't want to break the computational Diffie-Hellman problem. This kind of like avoids the need to break computational Diffie-Hellman problem. Okay, so this is the algebraic setup. Now we want to commit, right, to a polynomial f, right? So f is given by some coefficients. We want to commit to it via a single group element. So how do we get this single group element? Unfortunately, we work in this trusted setup setting. So we prepare a commitment key that will allow the prover to commit and verifier to verify. That is consisting of some, representations of a secret trapdoor evaluated on all the monomials that you can ever need if you care about a univariate polynomial of degree at most n. So I get t raised to the power 1, t raised to the power 2, t raised to the power of n, but kind of like hidden in the first group, and I get t, like the linear monomial, in the second group, right? So now if I have this commitment key, I have these very many group elements, I can combine them to represent evaluation of my polynomial f at the secret trapdoor without knowing the trapdoor. I just take the coefficients of the polynomial, multiply the elements of the commitment key by the coefficients, sum it up, and this will be a group element that exactly corresponds to the evaluation of f at the secret trapdoor. Never ever I had to know the trapdoor because I got those very many elements. So I'm gonna send over to the verifier this as a commitment, right? And this is exactly like the first point where KZG did something amazing, because we have a commitment which is a single group element, right? I started with a polynomial which is degree n, n being 2 to the 20, and I represented this via a single group element, right? So it's where the efficiency kicks in, and we don't have this in general, from other assumptions. Like when you want to have a polynomial commitment scheme, oftentimes, the size of the commitment depends at least on the log of the number of, of the supported degree. Good. So this is how we commit, and now we have these, nice representations of polynomials via group elements, and we will just use them to implement the check that we had here, right? So we want to check that f minus z is some quotient times x minus alpha. So this is what the prover will do, right? So it can compute the quotient polynomial, it will compute the representation of the quotient polynomial as the proof, and send it over to the verifier. And now the verifier, instead of the actual polynomial test, will do the group test, right? So it will construct c minus z, right? So that's the f minus z, and construct quotient times t minus alpha. Here the pairing comes in because, we need to do the pairing. You wouldn't be able to construct the group element unless you break the computational Diffie-Hellman, so you just do the test in the target group. That's it. Like, amazing, right? Okay. Now, so we have this very efficient scheme, and what is hard about proving knowledge soundness of this scheme, right? So if you want to prove just evaluation binding, that's nice for cryptographer. You get, two values, you get two proofs, and you can get out of it something that breaks some computationally hard problem. But now, if we want to extract a polynomial out of the commitment, we have a very hard time. So there is this extremely short digest of the polynomial, and I need to be able to explain it via a polynomial. So it's even worse, right? This is the ultimate thing that you face after you stare at these problems for a while. There is no polynomial, right? Because we are working against a cheating prover, and its behavior has nothing to do with polynomials, and yet we still need to explain it via some polynomial. Okay, so let's talk about not memes, but more of a theoretical notion of security, right? So we want knowledge soundness. In the reality, we have a prover and a verifier. They interact. The input is the commitment key and the commitment, and then the verifier asks an evaluation query, gets back value and the proof, right? And this gets accepted with probability epsilon. Then what we want is that if that there exists an extractor that's in the analysis, like a thought experiment, if we can submit many evaluation queries to the prover and get values with accepting proofs, we will construct a polynomial. What should be the property of this polynomial? Well, it should be consistent with the commitment, with probability that's roughly the same as the success probability of the verifier in reality. Okay, so this is the notion of extraction. If I have this like query access to the prover, I can use it in order to extract. Okay, with similar probability. It's very standard notion of extraction if you have ever seen any proof of knowledge, right? So now it's just applied to the setting of polynomial commitments. Okay. So a detour through the algebraic group model, right? I was saying that one of the first things that people did was they used the algebraic group model in order to analyze security, and that at best is a sanity check. Why is it at best a sanity check in this setting, right? So AGM was proposed by Fussbauer, Kiltz, and Loss in Crypto 2018, and people soon saw that it's a useful idealized model where we have algebraic adversaries. So there is like a depiction of an algebraic adversary. What is an algebraic adversary? Is somebody when when it produces something to you, it gives you an algebraic explanation for that. So what that means, like it got on input some group elements, it produces new group elements, so it says exactly how this group element was computed out of the input group elements. And like various papers, I think that the first one was Bonnet, Drake, Fish, and Gabizon in this ePrint note on how do you batch KZG. They defined a notion of knowledge soundness for polynomial commitments in the AGM and started proving that like various polynomial commitment schemes are knowledge sound in the AGM. So, and people do it to this day. Like there are newer proposals of polynomial commitments. They still use this as an analysis, but it has this bad feature that like all the proofs are kind of like one-liner proofs. Because you have an algebraic adversary, so it gives you, like algebraic explanation, and suddenly this is what you use for extraction. So the argument then is not very convincing. I think that in a formal way, like the only paper that touches this, why you wouldn't want to do it, is the TCC 2023 paper by Lipman, Parizela, and Thiem, when they introduced this newer extension of AGM OS, where they say, well, this sounds like a spurious knowledge assumption that you can extract from the commitment, and maybe you wouldn't want to do it, but like for now, it's not settled, like whether knowledge soundness in the AGM is very meaningful or not. Let me just, this was very high level, meta, AGM, algebraic adversaries. Let's be specific, right? So this is the univariate KZG, and you are working against an algebraic adversary, right? So the algebraic adversary got on an input the commitment key. These are just group elements that are the evaluations of the monomials, and then it comes up with a commitment. Right? What is a commitment? It's a group element. It has to explain it with respect to the commitment key. So it gives you some coefficients that you can use in order to combine the group elements to get the commitment. But by doing that, it gives you a polynomial, right? So you're done, like, no need for extraction. And this sounds like too little work for a meaningful proof of security, okay? So I hopefully soon we will have a more formal argument that shows that actually in the AGM the knowledge soundness as formalized currently is pretty much implied by evaluation binding by the much weaker property. So but the good news is that we can actually do extractability in the standard model, right? So let's take a look at it. How much time? It's fine. So univariate handled by Lipman et al. There's multivariate, right? If you don't remember anything after my talk, you will remember how these schemes work, right? We know how the univariate works, and the multivariate is like a very simple extension of the univariate one, right? So KZG had this nice insight. I take a polynomial, univariate one, I subtract z, it has to have a root at alpha so I can factor it out. So this is just a statement about polynomial rings. So you take a multivariate polynomial ring, now the multivariate one. If you subtract z, you're just saying that that polynomial, if the above holds, so that polynomial lies in the ideal generated by these linear factors. So you can like factor out all these linear factors, you will get quotients, right? So it generalizes nicely. So instead of like one linear factor and a quotient, you get, you know, like as many linear factors as variables and that many quotients, right? So we can again, you know, like turn the local test into a global test, right? And implement it via the same template as they did in KZG. So that's the PST13 protocol, right? Need to give you like slightly different commitment key so that you can commit to multivariate polynomials. The same idea. Now the trapdoor, right? I have trapdoor for each variable, and then you commit via computing the evaluation, the trapdoor, send it. How do you prove? Well, you compute the quotients, give the group elements that correspond to representations of the quotients, and you test slightly more involved group identity. This, don't be afraid of that. No alarm warning. Is just like a fancy symbol to denote the multiplicative operation in the target group. So, you know, like I have a sum which in the target group gets translated into a product of some group elements that we obtain after the pairing. But it's exactly the same and couldn't be like more beautiful. Good. So how do we prove the security? First, we do it, you know, like adults do it. We split the hard problems, right? So we take special soundness. I assume that I have very many accepting evaluation proofs, and they are on an interpolation domain. What do I mean by that? I have alphas 0 to alpha mu that allow me to, if I have the corresponding z's, that allow me to interpolate a multivariate polynomial that matches what I'm supposed to output. Okay, that's it. So I can interpolate a polynomial. Now the hard part is to show that the polynomial that I will interpolate is going to be consistent with the commitment, right? So this is where we need to do something. And I want to highlight, maybe I won't be able to tell you much more than this. So I want to highlight that we're working much harder than in the AGM. We need to submit many evaluation queries, but that's okay. We just need to like be successful on an interpolation domain. But then we still need to prove under some assumption that what we interpolate is consistent with the commitment. In the AGM, you get it for free, right? Like both the interpolation and the consistency. Okay, so how do you prove this? Well, what do I have? I have very many nice equations. So these equations are the verification equations of the verifier, and they attest that the commitment is consistent at some point with some value, right? So I have this like very spread information about the polynomial. I would like to aggregate this into, so I have very many of these equations. I would like to aggregate it into an equation where I'm talking about the commitment and the interpolant that I got from these alphas and z's, right? And you can do it, right? So there are two parts for that. So there's something that already Lipma et al. Called a batching lemma. We have like a more general batching lemma that works with multivariate polynomials, and that allows you to aggregate these equations. And then if you assume some problem is hard, you actually extract out of this aggregated equation exactly what you need to prove the consistency of the interpolant with the commitment. And that's the proof. So though like we don't know how to do it just from the univariate assumption, like maybe one could show that you cannot do it from the univariate ARSDH, but it's not that important. Okay, then yeah, so just like one word. 5 minutes? Okay. Do you actually have 5 minutes? Sorry.
11:40, right? Is that we're done?
Yeah, good. Yeah. Great. So let me actually talk about this. So how do you define knowledge soundness? And that depends on the application, right? One thing that you observe is that if you are actually interested in these PIOP2-SNARK compilers, then the use of the polynomial commitment is as a proof of knowledge of a polynomial, right? So this is what the prover is doing for the verifier. So the prover has a polynomial, and it wants to convince a verifier that it has this polynomial, and that's it. So verifier just samples some random evaluation point and couldn't care less about the value It just cares that the pi is like accepting, like I see like unhappiness. So 80% of the time, like in very many applications, of course, I mean, there are exceptions to this, but very many times, this is sufficient. And why is it good? Okay, so why do I settle for this? Well, because then I can invoke other people's results as a black box. And that's great, because in the paper of Lippmann et al., they relied on the Atema-Kramer-Kohl paper from Crypto21, their forking lemma. However, they had to take the proof of their forking lemma and somehow put it inside their proof of knowledge soundness. We can just, invoke the forking lemma as a black box, much cleaner. Okay, and yeah, nice thing is that, like for free, you prove knowledge soundness of very many variants of multivariate KZG. So multivariate KZG, okay, interesting for Hyperplonk, interesting for Spartan, but what people face in the reality, apparently, I wouldn't know, but so they have these monolithic provers. So there's like a huge machine that has to do all this work, and it's not very easy for practical instances to actually work with these polynomial commitments. It would be great if you could move to a distributed setting. So instead of like a monolithic prover, to move into a setting where you can distribute it into many machines and then maybe like aggregate, and this has been done. So there are the like pianist and hyperpianist variants that give you like a distributed prover for this multivariate KZG. Then the randomized multivariate KZG that we discussed that you need in order to have different binding properties. So all of the changes in these schemes are kind of on the side of the prover, cosmetic, and from the perspective of our proof, they don't matter. So for free, we get knowledge soundness even for them. So that's nice. Yeah, so summary is what I told you, right? We have this notion of proof of knowledge of a polynomial might be useful for you, knowledge soundness for many variants, and actually, when working with this, we have a better way how to write the quotients in the multivariate quotient decomposition. Might be useful for you if you want to use this and implement it, because it will allow you to parallelize stuff. So either talk to me or take a look into the paper. It's a lemma. You will find it very easy. Open problems, right? Clearly, do we need ARSDH, right? I don't want ARSDH. It's new. We proved that in AGM and GGM, it's okay. But what do I know, right? So do it from SBDH if you have the time. And another important question is: so people don't like multivariate KZG that much, because the proof size depends on the number of variables. So if you take a multilinear polynomial that represents a vector of size 2 to the 20, then you will have 20 variables. So suddenly, like, the proof size is 20 group elements, not good. So people proposed like what I would call a compiler that builds a multilinear from univariate, right? From the univariate KZG. It's like Gemini, Zeromorph, more recently Samaritan, and Mercury. As far as I know, all of these schemes have analysis only in the AGM. So, can you prove it in the standard model? Because we know that we can, right, like for other schemes. So that's it. We were supported by the Czech Science Foundation and also donation from Zirkit. I'm happy to take questions.
Could you please repeat how you proved that the interpolated polynomial was the one committed to without relying on AGM?
Right. So you have very many equations. That was this kind of right, and it's more complex than that. But you can somehow go, well, if you assume even something stronger, you can go directly from this to that kind of statement. And the point is that, like, these equations, they naturally like collapse to a one equation that talks about the interpolating polynomial, because you can just kind of interpolate over the equations, and then you will get exactly something like this because of, right, like the nice homomorphic properties of these commitments. But then okay, so you interpolate, but you will interpolate also over the second part of the equations, and here is where the ARSDH comes. So if ARSDH holds, you can simplify the right-hand side so that, you know, like basically stuff cancels out and you have what you need. So there's the two things. Like the batching lemma just aggregates, and ARSDH says that, you know, after you aggregate, you know, like unless the adversary is crazy powerful, broke some hard assumption, you actually have what you needed. Yeah, so that's how the proof goes. There was another question? Yeah.
Oh, yeah, thank you. What does the rational mean in this case?
Yeah, so there was RSDH, and so that's like, maybe we can take it offline. Like basically, like it's like an extension of the strong Diffie-Hellman assumption. If you ever saw that, so you just like get some polynomial in like inverse of the exponent. So that's like the rational part. And the adaptivity here is just that previously when people defined the rational strong Diffie-Hellman, they kind of fixed the polynomial. The adaptive means that the adversary can choose the polynomial. It's, you know, like, so you assume all that you need so that it works out. But it is different than, you know, assuming that the scheme is not sound, right? Because, you know, like there's still, like, it's only about kind of like aggregating the equalities in the end, you know, like so. Yep.
Question. Have you looked into the soundness of hash-based polynomial schemes like trie-based? Because there is now this, a couple of weeks ago, Ethereum Foundation did a bounty of $1 million for one of the lemmas about soundness of trie. So I was wondering if you would maybe know somebody who's worked on that, or you would.
Well, maybe like second hand through like some approaches how to instantiate these hash-based things, right? You know, this Ethereum Foundation has also like this Poseidon initiative, so that's also very interesting. It's more related to what Christian was talking about, like with this like lower level assumptions. But this is not going to tell you much about that, right? You know, like because it's inherently about pairing-based stuff. Yeah.
So can you repeat? ARSDHN is not the same in the multivariate case. It's a difference.
Yeah. So like there's like a natural univariate variant, and then with every variable you add, you get like a generalization.
Have you looked if there's any reduction from one assumption to the other in the AGM or whatever?
Yeah. So you have like a hierarchy basically, like but we don't know how to separate for now, and like. I think that AGM and GGM, they don't completely allow you to differentiate that well between these particular assumptions. That's what we kind of learned. We're like hoping that you would actually show that they are different because you get different bounds, but it's not the case. Like you prove the security of ARSDHN under basically the same assumption in AGM as for the univariate case. Because, you know, like some suitable FPR. So.
Yeah, like you end up with an assumption of the order of the number.
Yeah.
And yes, I'm curious if you have some thoughts about these relations between multivariate and because.
You mean like the last thing that I mentioned? Yeah, this.
Yes.
I think that, you know, like that. Okay, don't quote me on that, you know, but it should be easy. I don't understand why they themselves didn't, you know, like prove it just by a reduction to knowledge soundness of the univariate. But you know. Okay, so maybe they didn't consider that problem solved, right? So they went right away for an analysis in AGM, but, you know, like, okay. Samaritan and Mercury, that's what I looked at like carefully. Gemini and Zeromorph, you know, like I'm not going to comment on, right? You know, like, so those are like involved papers. Zeromorph is involved, right? So, like. Any questions?
All right. Thank you very much.